Assalamualaikum warahmatullahi wabarakatuh. My name is Muhamad Haniff bin Rameli. I am semester 7 student and currently being supervised by TS Muhammad Fauzi Othman and Prof Madya Dr. JURI SAEDON. I will present proposal for my project, which is influence of process input parameters on axial cutting force during ultrasonic assisted milling of borosilicate glass through ductile mode and brittle mode mechanism. This is the presentation outline that I will explain later on. First of all, I will go through project summary. Ultrasonic assisted milling UAM is non-conventional machine that remove workpiece by vibration of high frequency tool. This method is suitable for conductive material, non-conductive material, hard and brittle material in nature. My choice of material is borosilicate glass, which is brittle and difficult to manufacture. The topic will cover about influence of process input parameters on borosilicate glass. Mathematical model will develop to assist the prediction of axial cutting force for ductile mode and brittle mode mechanism without doing actual experiment. As we know, borosilicate glass is frequently used in biomedical devices, optical lens, aerospace, automobiles, and others. Borosilicate glass has high durability and resistance toward chemical change. Structural bond of borosilicate glass contain silica, boron oxide, and alkali, make it more durable toward chemical reaction. Mechanical properties of borosilicate glass make it difficult to handle, especially when using conventional machine. Through experiment and research, it is said that non-conventional machine is the proper solution to tackle hard and brittle material. UAM operate by combines the milling kinematic with grinding material removal mechanism along with the ultrasonic assistant that enable it to vibrate vertically along its z-axis. The mathematical model is proposed taking consideration two different material removal mechanisms, which are ductile mode and brittle mode. As for the literature review, I will focus on past research paper about ductile mode and brittle mode. From paper published by B.K. Engoy and P.S. Serge in year 2000, they prove that ductile mechanism will produce formation of plastic flow in form of sheared machining chips. There is a term called ductile regime machining that stated if size of plastic deformation is too small, the material will deform plastically. For mathematical model, Y.L. Taibani and H.L. Hofi in 2019 proved that ductile mode can be related to Hertzian indentation theory. Concept of Hertzian can calculate indentation depth into surface within specific range. Further explanation about this theory will be explained in methodology. Next, for brittle mechanism, material removal will form lateral crack and medium crack. It is said that this crack act as sharp indenter to remove material. This research was done by Ostojic and P. McPherson R. in 1987. Y.L. Taibani and H.L. Hofi once again prove that viscous hardness theory is suitable for brittle mode mechanism. Hardness H as deformation parameter showing medium crack development, while toughness K as fracture parameter evaluate strength level in material. Detailed explanation also will do in methodology. Next, I move to the problem statement. Borosilicate glass is desirable material because it has many use in industry, as I mentioned before. But it is a material that difficult to manufacture and handle, especially when using conventional machining, because it is easy to fracture. Hence, how to predict axial cutting force on borosilicate glass by using non-conventional machining and different process input parameters. This purpose to ensure high quality surface product can be obtained and increase productivity. Next, the objective of this study is to perform mathematical modeling to investigate the influence of process input parameter on axial force in ductile and brittle modes. Second, to predict the value of axial cutting force for both mechanisms without doing actual experiment. The results obtained will be verified with previous research to prove the experiment. Third objective will be covered on next semester, which is to make analysis on the trajectory movement of ultrasonic machining in 3-dimensional. As for the scope of this project involve literature review on past research paper to collect information and for the model verification. Next, understanding mathematical model development for ductile mode and brittle mode mechanism to predict axial cutting force. Then, develop coding of mathematical modeling into MATLAB software to get the results. For the limitation, this project cannot do actual experiment because of high cost for machine and the material. Safety factor also considered because of pandemic COVID-19. Next is methodology. This is full flowchart process for mathematical development that I will explain briefly in 4 main steps. But before that, what I need to highlight here is the abrasive diamond grain particle are assumed to be spherical in shape. Hertzian contact theory is applied for ductile model and viscous hardness theory is applied for brittle model. Only 45% of active diamond grain participate in cutting process. In addition, cutting tool in this experiment are assumed to be perfectly rigid. Step 1 is to understand the relationship between single grain force and grain indentation depth. This is where the ductile plastic deformation of Hertzian indentation theory is applied to ductile model. Equation for indentation depth from Timoshenko and Godier in 1970 is simplified in terms of contact force Fn. Meanwhile, the equation of indentation depth for brittle mode came from B. Long and R. Wilshaw, which is viscous hardness theory. Same as ductile model, the equation is simplified in terms of contact force Fn. Step 2 is to understand the relationship between UAM cutting force and single grain force. So, left image in the slide shows the number of grain face and side equation. Both equation will be multiplied by 0.45 assuming the active grain. The modeling equation of effective cutting time is done based on the sign graph by assumption made and simplified into final equation as shown in figure. Step 3 is to estimate actual volume of material removed by 1 grain indentation U and calculate material removed volume W from relationship between input variable and material rate removal MRR. As for ductile model, the indentation volume U of diamond grains penetrating into the workpiece is the intersection between intended spherical diamond grain and the workpiece will be part of ellipsoid. So, the indentation volume is calculated by the integration as shown in step 1. While equation of remove volume W that relate with input variable of feed rate and depth of cut is obtained from equation MRR by simplifying in terms of W. Then, step 3 is equaling equation U and W. Lastly, simplify in terms of indentation depth delta, the equation is obtained as shown in figure 4. For brittle mechanism, according to the sharp indentation theory as shown in the figure in the slide, the equation of lateral cracks and head of cracks, where KLC is the fracture toughness of workpiece and HV is workpiece hardness. K2 is dimensionless constant number. The indentation volume U for brittle due to the brittle fracture is simplified 2 times the volume of tetrahedron ABCD as shown in the figure. By equaling equation U and W, final equation of indentation depth delta for brittle is obtained as in step 4. Final step is obtaining UAM model cutting force, where you can see is the multiplication of contact force Fn, number of grain phase, effective cutting time, and vibration frequency for both ductile and brittle mechanism. Next is the expected results. The result will display relationship of process input parameters with axial cutting force, and MATLAB software is used to plot the graph. First, for ductile mode, as we can see, if the spindle speed increase, the value for axial cutting force will decrease. This is because chip thickness decrease, leading to lower cutting force. For case of feed rate and depth of cut, both increase with the axial cutting force. As feed rate increase, the relative cutting arc length become longer, and the machining loading increases, causing higher cutting force. The increasing the depth of cut increase the volume of the removed material, which in turn increases the corresponding cutting force needed to remove the material. The pattern for plotted graph for brittle is same as in ductile mode. For spindle speed case, axial cutting force decrease while spindle speed increase. Both feed rate and depth of cut increase with axial cutting force. The reason for the result also same as in explanation in ductile mode. Next, for comparison between ductile mode and brittle mode mechanism. As we can see in all the three graphs, ductile mode produce higher value of axial cutting force compared to brittle mode. In case of ductile mode, the specific cutting energy increase as the indentation depth increase, leading to increase the axial cutting force. Whereas in case of brittle mode, the cracks initiate, propagate, and intersect, thus weaken the material strength, which in turn decrease the axial cutting force. Before I end my presentation, I would like to show you my planning for this project in this semester and next semester. Alhamdulillah, I managed to follow up my planning as shown in the Gantt chart for this semester. Inshallah, for the next semester, continuation for my project will run smoothly. That's all from me, and thank you for your attention.